下面有请 Red Hat 工程师 Michael 和Vikhyat， 他们分享的主题是常见的问题支持以及如何对他们进行故障排除。
Good afternoon, everyone. I'm Mike Hackett, Principal Software Maintenance Engineer with Red Hat Ceph Storage. It's my colleague, Vikhyat Umrao, also a Principal Software Maintenance Engineer with Red Hat Ceph Storage. Combined, we've been supporting Ceph for 7 years, so we've been along for quite the ride with Ceph Storage. What we're going to cover today is some common support issues that we've seen over the last 4 or so years supporting Red Hat Ceph, and what you can do to look into troubleshooting these issues and resolving these types of issues. The 2 common topics we're going to cover today are 2 of the issues that customers log with us. This is coming from a larger presentation which had upwards of 80 slides in it, and we cut it down to about 20 slides to cover these 2 issues. We're going to cover slow block requests, cover what is a slow request, possible causes of these, different types of slow requests, and what you can do to troubleshoot them. Includes looking into hardware using Linux utilities and finding common trouble spots with these. Also, we're going to cover flapping OSDs, causes when using object storage with Rhinos Gateway, where there's millions of objects leading to monitors dropping OSDs. Same thing, we're going to cover where can we start looking, some possible causes, temporary solutions for alleviating these, and then also permanent solutions to alleviating these types of issues. The dreaded slow request. Anyone that's been running a Ceph cluster for a period of time will have seen slow requests logging in that cluster. So what is a slow request? Basically, when Ceph detects a request that has taken too long to process, we flag it as a slow request. By default, that's 30 seconds. That's adjustable via the config option, OSD op complaint time. Keeping it at 30 seconds is recommended due to if you decrease this or increase this, you may be seeing false positives leading to actually having slow requests log when there's actually no issues being seen by the end client server. Slow requests log accompanied always by block requests. Okay, for some examples of what you're seeing over here, if you've been working with Ceph for a while, you'll be familiar with seeing these pop up every now and then, as sometimes scrubbing is occurring and stuff, we may see stuff like this. So highlighting some of the possible causes of why we could see slow requests logging in a Ceph cluster. Problems with underlying hardware, disk drives, overutilization of disk drives, older disk drives, any issues with controllers, whether it be a driver firmware issue with the controller leading to these types of issues. Host or kernel configuration, for example, improper setting of kernel PID values, FD limits, things along that nature. And then racks or networking equipment. That can be any combination of MTU misconfiguration, ports in the network switches going down, or overutilization of the network equipment. That leads into a system load, basically just pushing too many reads writes to the system that are overloading either CPU, RAM, or your OSDs, your backing disks. Improper configurables set on OSDs, for example, file store op threads, OSD op threads being set too high for your hardware to handle. It's common scene when you're going to tune your cluster and you're like, oh, if I can set file store and op threads and that'll improve performance of my Ceph cluster. You're going to jack those up to a higher count, and turns out your hardware can't handle it. Custom configuration issues. This is common with improper PG count settings on your Ceph pools. It's going to lead to imbalance throughout the cluster and OSD nodes taking on more data, more reads writes than other OSDs in the cluster. Cluster on the backfill or recovery. OSD goes down, backfill recovery is prioritized. We can see slow request logging due to the churn that we're getting from recovery op threads. Also deep scrubbing. We know that when deep scrubbing is occurring, we lock those objects at the time the deep scrub that's occurring. We can actually block an IO that's coming to a specific object that's being deep scrubbed at the time. There is a work coming up in Luminous where we actually have a preempt deep scrub. Vikhyat's going to talk about that a little later, where we actually prioritize the client I/O. We'll back off the deep scrub, let the client access the object, and then resume the deep scrub once the client's op completes. Most recently, a lot of the stuff we've been seeing has to do with compaction and splitting occurring in the OSD node, file store level splitting, and then level DB compaction with larger object workloads. Common types of slow requests that you generally see. Waiting for read-write locks. Basically, this occurs when there's an in-progress op on the object in question, and the backing up is waiting to require a lock. So for that previous write to complete or operation to complete, and for that object needs to wait to require that lock. This can be due to several issues. These are some of the tougher ones to determine what the actual cause is, because it could be anything from networking on a specific node, leading to delays in releasing the ops on those objects, or it could be a misperforming disks that could be leading to the same exact type of situation. Waiting for sub-ops. So this is triggered when, say we have a replication value of 3. So when we're waiting, the primary OSD is waiting for our sub-OSDs to process the write from the journal. We don't report the act back to the client until our final replica copy has processed that write. So when we're waiting for sub-ops, this may usually be due to other OSDs in our replica sets either being on a slow node, either having a slow disk, an overwhelmed disk, things of that nature. No flag points reached. So this output is basically when the operation has not reached any major flag points, whether it be queued for PG or something of that nature. What we usually see here is a large backup in high CPU utilization. So if you look at like a Linux utility such as PerfTop, something along those lines, you can see the CPU running 80% and usually more utilization. Waiting for degraded object. So basically the OSD is aware that an object exists, but that object hasn't been replicated a specific number of times per the replica value set in the pool, so 3 for example. This is the only type of slow request which will actually block the I/O to that object. So some common troubleshooting techniques. So this is the bones of this presentation. What can we do to determine what the actual cause of the issue is, whether it be physical, hardware, networking, things of that nature? So obviously, first place you always want to start when you're looking into any type of issue log in the Ceph cluster is just have a look at your Ceph status, your Ceph health detail, to see if there's any backfill recovery occurring in the cluster, any types of OSDs that have gone down, and are slow requests even logging. So start off with a Ceph-S or a Ceph health detail, and that'll give you more general idea of where you need to look. Another thing is we can determine the OSDs logging the slow requests. Do they share any type of common piece of hardware? Are they in the same storage node? Are we in the same rack? Are they sharing the same network switch? That usually can help us. So if you have a large number of OSDs logging slow requests, but you've determined that they're all sharing the same piece of hardware, such as a storage node, then we can just set that storage node down in the cluster, and we should be able to service the requests across other OSDs. Verifying disk performance on OSDs logging the slow requests. We can use Linux utilities such as IOstat, look for high utilization or high wait times against specific disks, and that'll usually help you determine cause for the slow request, basically an overloaded disk. Usually when we see these types of issues, we can look into, it could be a single OSD logging the slow requests, or we could have a number of OSDs logging the slow requests, and we've narrowed it down to a single node, do an IOstat on that node. We're looking at the node and we're seeing 80, 90% utilization, and await times up in the 600 ranges, and the disks just can't process the I/O quick enough. So we back up in the Ceph cluster. Another common useful thing we can look for is network performance or throughput errors. So anything seen in the NICs, retransmits, any possible changes in the network, maybe an admin made a change in MTU or something along those lines, kind of feeds into the next point. Jumble frames, so just verifying from a network standpoint that your networking equipment can handle that frame type size. MTU sizes need to match throughout the environment in order to successfully pass frames, so that's also a common issue that we've seen in the past. Utilizing ifconfig or ping with a specific frame size is what can be used to determine if network is the cause for that. Determining if deep scrubbing, compaction, or splitting is occurring at the time of slow requests can be looked at as well if none of the above fits your issue for disk performance, network, or anything along those lines. Ceph.log file will tell you if a deep scrub is occurring against a specific OSD, give you that time frame, and then you can see if the slow request was logging at that time frame. Compaction or splitting would be a little more difficult to determine, although with later releases of Luminous, we actually now log file store level splitting with the default OSD log level of 1, so we will actually log when splitting is occurring, which makes it a lot easier to determine if splitting is actually occurring at the time of your issue. A handy tool we use is called the Ceph log parser. This is available on GitHub. It was written by another one of my colleagues at Red Hat. The Ceph log parser can be very handy when determining tough to find out slow OSD issues. Lots of times when we get a slow request and we're logging against a single OSD, that's easy to determine that it's that disk that's backing up the cluster. What we had issues with in support was when we were seeing multiple OSDs spanning multiple nodes logging slow requests. That's when the problem of root causing these issues occurs, because there's no clear piece of hardware causing the problem. Because maybe one OSD was logging slow requests and other OSDs in that replica set were only logging slow requests because of the original OSD that had the problem. What this log parser tool does is basically you can feed it an OSD tree, which basically takes into account the crushed leaves where our OSDs and our Ceph nodes reside. And we can feed it a Ceph.log file. And we run the parser, and it'll give you a nice output, such as the example that you see down there. I'm sorry, it's a little small, but if you have copies of the slides or you want to use it, you can have a better view. And we actually show you and we log the number of types of slow requests that logged, the crush root that's actually logging the slow requests, the OSDs that are logging the slow requests. So it gives you a much easier, high-level view of where the issue actually lies. So that's it for slow requests. Vikhyat is going to cover flapping OSDs, and this is something he's been very familiar with over the last couple of years.
Thank you. Thank you, Michael. Let's talk about flapping OSDs. So what is flapping OSD? So mostly in Ceph, we have two types of networks, which is called public network and the cluster network. So public network is nothing but where all the clients and monitor resides, and OSDs talk to each other with their peers in the cluster network. What happens is that when two OSDs or three, as per the replica, they talk to each other, and if one OSD is not responding to another OSD, and if that happens for multiple OSDs, if any two OSDs which are peer to that OSD which is not responding informs back to the monitor that this OSD is not responding to me, monitor mark that OSD as a down. And if that OSD is not down and the PID is still up, it will bounce back and it will say that you have marked me wrongly down. But if the process really went down, the OSD will go out, which is default 300 seconds. So the default value which is controlled by the tunable, which is called mon-OSD min-down reporters, you can increase it to the number of OSDs in one node plus one, so that you can come out of false positive. So that you need minimum one node OSDs to inform monitor that okay, these many number of OSDs are not responding to each other. So this is how a flapping OSD, like OSD goes down and comes back. This is nothing but the flapping OSD. Now let's focus on why, with the large number of objects cluster for the RGW workload, why we see flapping OSDs sometimes. So let's just, where to start? Let's identify the workload. If you have large number of objects, it means that you will be having loads of puts because you are writing a lot of data to the cluster. That's fine, but if you have deletes in the same ratio, like if you have, let's say you are writing 80% of your workload is write, and in parallel you are deleting 60% of data in the same amount of time, it can cause this kind of issues. I will be covering in the next slide that why a delete workload can cause this issue. Check the bucket in the sharding, which is used or not. So in RGW there is a concept of bucket sharding, which is nothing but shard your index objects for each bucket, and to check the that your bucket is sharded or not, this is the command. If the value comes as a 0, it means that your bucket is not sharded, and this is the default. And if this has some value in the terms of 2 power, so like 32, 16 or 64 or 128, 256 like that, so you will see that's a sharded bucket. And the third thing you need to check is that your index pool, Rado's index pool, is backed by SSD or not, or NVMe. So these are the 3 symptoms which you should verify that your cluster is coming under any of these 3 or all of these 3. And if it is coming under any of these 3 or all of these 3, it means that you have some problem. So what are the possible causes? The first issue here is that when you have millions of objects, the label DB, the OMAP backend for that OSDs, it grows like anything, like because each index gets stored into the OMAP keys, and OMAP keys are nothing but your label DB key value pairs. Now what happens that if you run operations like deep scrub listing of the bucket, it needs to read all the data from the OMAP. And as much as data you have in the cluster, that many number of keys it has to read. And if it is your index is not sharded, it means that it is going to add more pain because your index object would be very, very large. I'm going to cover in next slide that how you can calculate the object size. The second issue is that what I talked in the previous slide, like delete workload. So like when you have delete workload, it causes lots of stale data in the OMAP. So what happens is that you deleted lot of objects within a bucket or within multiple buckets. It will remove all the entries for that from the OMAP keys. But the label DB is not like that, that whenever you remove the data from bucket, it does not free up immediately the keys in OMAP or in the label DB. There is a threshold in label DB which only when it is hit, then only it will trigger the compaction to remove all the stale data. And if you have lots of stale data, it would be always compacting. And as Michael covered, compaction is a very, it's lot of CPU and intensive and the disk intensive operation. So what happens is that it starts causing issues to OSD because it will be always compacting and it won't be allowing OSDs to perform the I/O to the cluster because most of your CPU cycles and the disk cycles would be busy with the compaction rather than taking the client I/O. So these are the 2 possible issues and reasons why you can see you have OSD flapping, because your OSD is either compacting the label DB or the deep scrub option or client I/O listing kind of I/O is always keeping OMAP, it is always reading the OMAP keys. So till Joule release or before Joule release, the OMAP backend, the OSD default OMAP backend is label DB. And any Luminous cluster which were upgraded or which are being upgraded from older releases to Luminous release, they will still have the label DB. Any cluster which is deployed newly in Luminous, they will have label OMAP backend as a ROX DB, which is pretty good because it uses a multi-threaded compaction and lot of other enhancements like Bloom filters and all that thing in RocksDB. With labeled DB, the drawback is that it doesn't use multi-threaded compaction. It's single-threaded compaction. It doesn't have those features what RocksDB has for improving the performance. So what would be the temporary solutions? As soon as you see that you have lots of and millions of objects in your cluster and you see this issue, maybe you have a production down, like because your OSDs are flapping and the client IO is not reaching to the OSDs. And you will have always backfill recovery going on in the cluster because OSDs are flapping. And as Michael covered, that you will see the waiting for degraded object or waiting in pairing, because your OSDs is going up and down, the flapping, it will trigger the recovery and pairing. And these are the two operations where we block the IO, because we have to be consistent into the data. We have to be in consistent state. So what happens is that your customer will immediately start shouting like, my clients are timing out. My application is not able to get the data from cluster. So what would be your immediate solution to solve this issue? The first thing is that if the DB-scrub is running in the cluster, so there are two things. Either you can set the no DB-scrub flag globally, if it is a hammer cluster, till hammer, because the feature for setting the no DB-scrub flag to particular pool came in June release. So, and the command is that Ceph OSD pool set pool name and the no DB-scrub equal to 1. So this will take care of setting the no DB-scrub flag only in index pool. Now how it will help? As soon as you will set it, there won't be any no DB-scrub going on to the index pool, which is causing the OMAP to read again and again. That is the first temporary solution you should do immediately. After that, if this is not helping, then there are timeouts value which are very much configurable. Those are OSD op threads and file store op threads and recovery op threads. So what happens with them? If you see that in the OSD logs, after setting the no DB-scrub flag, still the OSDs are flapping and they are timing out. So what you do, go ahead and increase the timeout values like this. So these are configurable. You can use a cephtail command to inject them dynamically, but it is highly recommended to put these values in ceph.com. If you don't put ceph.com these values, what will happen? If OSD goes down and comes back and the PID gets killed, when the OSD will come back, those new values won't be in memory. So to keep this value as a consistent when you are troubleshooting this issue or when you are helping your customer or users, definitely make sure that these values are in ceph.com. And these can be injected via inject-star also. So for op threads, you have OSD op threads. That's the timeout of the thread. But after that, there is a suicide timeout. So OSD tries to keep up that much of number of time. But if it's not able to work till that time, what it does, it hits the suicide timeout and it kills himself, so that it doesn't harm to the cluster. That's when it goes out, and that's when the PID goes away. So you have to make sure that you configure the op thread timeout also and suicide timeout also. And the third temporary solution, which is very important, you should be doing the compaction. That's called offline compaction. This helps to remove all the stale data from the OMAP, from the labeled DB, because once you do offline compaction, it helps labeled DB to compact and then OSD to boot. So it doesn't have to compact always again and again. And we have seen that OMAP DIRs, which are more than 50 gigabyte, they come down to 10 or 5 once you do offline compaction. Because for offline compaction doesn't need a threshold to meet. You are manually telling the labeled DB to compact the whole thing. Permanent solution. So I was talking about the size of the index shard, how you can calculate it. So you can use the Rados low level command, choose one of the index shard object from the Rados and run a wtc-l command. It will give you the number of keys inside that Rados index shard, and each shard is nothing but 200 byte. You can multiply it, you will get the size of the object. that Rado's index shard object. If it is greater than 20 MB, it means that definitely you need to reshard your bucket. We have seen the objects like 1 GB or 500 MB sometime. So the recommendation is something like you reshard your buckets. There is a feature in Luminous which can take care of dynamic resharding. But if you have very good production cluster, it is highly recommended to take a production downtime and you can do offline resharding. And use a proper recommended value like 100 and 1000 objects per shard with your future growth keeping in mind. Then if you see that your all the index pool OSDs are backed by that pool are always disk bound, you consider them migrating to the NVMe or SSD, because then it would be very faster to compact them, the level DB, and or it's RocksDB, whatever. So they will have more disk cycles. And if it is always 100% CPU bound, then consider to migrate to RocksDB. Joule still do not have support as a OMI backend as a RocksDB. This PR is being worked, and I think it soon should be merged into 10.2.11 or 10.2.12. So Joule will get the RocksDB support. So what should be the how you can migrate from level DB to RocksDB? These are the steps which I have listed here so that you don't have to refer to the external documentation. If you use them, it should be all set. You should be able to migrate it. And if you don't want to use these steps, you have another option which is called file store OMI backend RocksDB. You can rebuild the OSD. In summary, if I cover, make sure that you have index pool for a production large cluster. Make sure your index pool is backed by either NVMe or SSDs. Have a proper bucket index shard. Set a nice value taking care of your future growth like these many with the 100 and 1000 per shard object. And then have index pool SSD to use RocksDB, which is default 8 compaction thread. And compression disabled, and the RocksDB cache should be tuned properly. And one thing which Michael talked about, the preempting the deep scrub, this is coming in Luminous. So now whenever you have a client IO coming to a deep scrub object, the deep scrub IO would be taken back and the client IO would be loud. So this is coming in Luminous. That's it. You want to cover this? Yeah, go ahead.
This is just a book plug for our recently released book that we did for some Ceph recipes and things along those lines, VM recipes. Thank you very much.
Thank you very much.